So we're gonna talk to you about the case for dark matter in part one of a series of 2 lectures. WIMPs are weakly interacting massive particles, and we'll tell you where they fit in to this story. So just a quick overview. In tonight's lecture, we're going to cover astrophysical evidence for dark matter, what the dark matter might be, and first look at the experiment that we're just in the process of turning on. And then next week, we'll do a very quick recap and then talk through some of the technical foundations of the basic particles that we're trying to detect, and the ones that we use to calibrate the detector, and the ones that we want to shield and get rid of. What's the basic particle physics of how particles interact with matter? Because that's going to be at the key of detecting them and shielding the detector from them. We'll then talk about the detector design principles and give you a brief survey of some of the different dark matter experiments around the world. And then we'll go back and talk about LUX in a little bit more depth, since we'll hopefully have provided you with a foundation to understand what the data that we're going to be taking in the next couple of years, what that data is going to look like, and what we'll be able to learn about dark matter from those considerations.
Okay. So we're about to tell you all about why we think the universe is full of dark matter. So, which is kind of an outrageous claim in a lot of ways. And just sort of orient us, start with this sort of view of things, which for physicists is absolutely natural, that the world is mathematical. And so actually, since we're physicists, we'll start back with Newton. You go back to his time, and there he was about 20 years old, and he was home because the plague closed college, and he invented physics and calculus in that year. And just going back all the way to him, you see this diagram over here. He was thinking about things. You throw a ball, it lands, and if you throw a ball harder, it goes further. And then he's like, well, if you throw it hard enough, and you think about the whole Earth, there's some perfect velocity where it'll just keep orbiting. And then he derived, laws of motion. He derived the laws of motion, and there he was, sitting in his home in 1665, and he's written down something which basically describes, his famous force law for gravity, and the calculus gives, sort of how you calculate the results of that force law, and he's derived how the Earth orbits the sun. I mean, this is incredible, right? That you can mathematically write down something like that, and what he wrote down is perfectly right. We were able to put a man on the moon according to those, just those physical laws. And if there's any doubt that physics works, I mean, this should put it to rest. I mean, the world is resolutely mathematical, and the mathematical results that we've developed explain things. Now, so we're doing an experiment in South Dakota. In South Dakota, one of the things they like to do is play with snowmobiles. See if you can see that. It's a person doing a backflip with the snowmobile. The equations of motion for that, can be derived mathematically. You could know you'll stick the landing if you launch at the right, launch your snowmobile at the right velocity.
The idea for dark matter is to look for sources of gravity, and so and see that the systems that we can look at on astrophysical scales follow these same laws. So if we apply Newton's law of gravity to the solar system, we can use it to see if there's a self-consistent picture. Okay, so you can make a graph of the orbital speed of a given planet as a function of its mean distance from the sun. So gravity is a force law that as you move away from the source, which is some massive object, the strength of gravity falls off like 1 over r squared. Okay. Now, for an object to move in a circular orbit, there has to be a centripetal force, a force that causes it to constantly be turning towards the center. Okay, so just like twirling a ball on a string, where the tension is in the string is the centripetal force. For planets moving in the solar system, the sun's gravity is the dominant gravitational force. So you can more or less ignore the gravitational interaction between the planets and just focus on the sun, since it's 99% of the mass. So as you move further and further away from the sun, the strength of the gravity is falling off, which means the centripetal force is less strong, which means you can only sustain a more slowly moving orbit, right? So gravity makes sense in the context of the planets in the solar system.
So, so the amazing thing is that Newton's version of gravity, and then Einstein modified it with general relativity. Those things work perfectly in the solar system. And in fact, this isn't on the slide, but we've tested Newton's gravitational laws down to the fraction of a millimeter scale. There are now precision experiments between two little things where you can measure the force of gravity between them. It's a very weak force. All of you have gravitational forces between each other, but they're much less than the attractive or repulsive forces, the sociological forces that exist, right? But they are there, and they're just sort of negligible. But with really fancy experiments, people are able to test gravity at the millimeter scale, up to the scale of the Earth, up to the scale of the solar system. And those are vast distances, a vast range of distances. And yet, let's look at the next thing out, which is galaxies. Galaxies huge compared to the solar system. And this is the same sort of graph that Dan showed just a moment ago. There, the sun was in the center and things were orbiting. Here, for a galaxy, here's just a photo you can grab with Google Images of a galaxy. There's the center, and there's stars, and it's a whirlpool. It is indeed rotating, and by Doppler shifts, you can measure the actual rotation. It's moving very slowly. In your lifetime, the galaxy won't move in a way that you can see it do that. But if it's edge on, you can measure the motion with sensitive telescope. And in fact, it turns out there's objects, sort of gas clouds outside the visible edge, and you can measure further and further out, okay? And this graph is all about what you see. If a galaxy is about like that, the visible part from the center out, so from the center out, is to here somewhere. And in the middle, it's not quite like the situation with the sun and the planets, because it's a bunch of mass. And that force law that Dan described nicely that had the simple shape, that was when there's one mass in the center and you're outside of it. And that's not quite the situation with a galaxy, but with a computer, you can kind of do the averaging calculations and calculate what should happen with this galaxy. And again, this is how fast something's whizzing around, whirling around, given how far it is out from the center. And there are objects out here you can measure, and this is what you would calculate given the amount of sort of gas and stuff that there's still some mass in the galaxy out there, but things out here ought to be rotating more slowly the further out you go. And this is out to maybe, say, 10 times, it's sort of out here somewhere. And this is the measurement. In stark contrast, the velocity of objects measured sort of out beyond the edge of the galaxy is about the same, even when they're quite far away, about 10 times out past the visible edge. And this is seen initially maybe in the 60s, maybe in the 70s. 70s is when an astronomer named Vera Rubin really tried to look at this systematically. It's not an easy measurement. You got to find a galaxy that's doing the right thing. Hundreds of galaxies were measured then, and since then thousands. Every single one has this very strong deviation between what's expected and what's measured. The things outside are moving faster than they should, given the amount of gravity holding them. And there's maybe two explanations. One is that maybe gravity works very differently on these extremely large scales beyond the solar system. But we don't know for sure, but we tend not to think that, or many people tend not to think that, given that it worked perfectly on the scale of a millimeter up to the size of the solar system, which is a huge scale range. So what we tend to think is that there's a bunch of mass associated with this galaxy that we're not seeing. It's not emitting light, and it's not shadowing light. You can look in all wavelengths. There's no evidence of any mass doing anything. That means not dust, not gas, not planets, not stars. And because it's not emitting light or shadowing light, we call it dark. So that's dark matter. And this is the first evidence for dark matter, was essentially every galaxy for which we've been able to take that sort of measurement of the speed of it rotating.
So now the next thing out after galaxies is clusters of galaxies. So these are, so this object here, if you will, each of these yellow blobs is itself a galaxy. And these things are orbiting each other just through their mutual attraction. So not quite the central object with everything, tailing off, but still what we would call a bound system. Things are not flying in or flying out. They're staying, roughly in some sort of spherical bound distribution. Now, occasionally, one of these clusters of galaxies just is perfectly aligned between the Earth and some very bright, distant background object. And what we learned from Einstein as he kind of advanced beyond Newton's understanding of gravity is that very strong gravitational fields warp the space around them. We talk about, this comes from the ideas of general relativity. So we normally think in terms of like a photon would travel in a straight line. But if it's traveling near a strong gravitational field where space is bent, it will be lensed. It will sort of scatter around the object that's bending space. And so one of the reasons we like to show this is kind of a cool image from the Hubble, where this object in the background that's slightly blue is being split into multiple images. Okay, it's literally being lensed by this intervening cluster. So now we can play this, dark matter game again. We can ask, well, the total mass that's present is going to determine the strength of the lens, whether we can see that mass directly or not. Separately, we can add up all the mass associated with the objects that we do see, and astronomers are good at calculating this thing called the mass to light ratio. So by studying how much luminosity, how much brightness is coming from this thing, they can say, well, this is the luminous mass. And then by measuring the strength of the lensing, they can come up with the so-called dynamical mass, the amount of mass that's there literally bending the space around it. And this graph here is sort of a iterative sort of computer calculation that shows you what the distribution of mass must be to generate the lensing that's observed. So you can see each of these spikes represents, one of the galaxies that's causing this thing to be sheared around. But that's not enough to explain what's going on. There has to be a smooth sort of distribution of mass that's about, I think it's a ratio of about 30-to-1 of this smooth dark component compared to the galaxies themselves that's needed to explain the strength of this lens. And so it's even on these larger scales, we continue to see this pattern where most of the stuff is not directly visible. It continues to be this dark component. Now, this is kind of the modern way of studying the dynamical mass or the amount of dark matter in galaxies. Even before the galaxy studies themselves, Fritz Zwicky was a contemporary of Edwin Hubble. He was studying just the speeds of galaxies in a cluster. And just by the rate at how fast they were whizzing around, he got the first glimmer of that there was dark matter. So this problem that we're studying and could possibly answer in the next few years is an 80-year-old mystery problem, an 80-year-old mystery. We still don't know what this stuff is about. And the time since then has been kind of studying, okay, well, what's the next least crazy thing that we could go look for? Oh, we didn't find it. All right, what else might it be? And so that's kind of how the story is going to unfold. Should I do this? Okay. So an interesting part of the story is that we need to look at how the universe as a whole unfolded. And so the framework that we make sense of all this stuff in is the Big Bang itself. So the idea that the early universe was very hot and dense. Particles were created in this hot plasma. The universe cooled, atoms formed, the universe became transparent to light. Eventually galaxies formed, and then us. So this is the sort of the intellectual framework through which we're going to try to make sense of this question.
In a cluster, does the dark matter surround the individual galaxies, or is there a dark matter halo that would encompass the entire cluster?
In the cluster, it seems to be a smooth component. And in fact, our understanding of this, there's a simulation that we'll show you in a minute. I guess that's actually of a galaxy, not a cluster. But the way gravity works is that sort of the rich get richer. And meaning that the regions that start out dense in the early universe tend to attract more matter to them. Okay, and because of how the dark matter works versus the ordinary matter, the dark matter tends to clump first. So that smooth component of dark matter was probably there first. Ordinary matter tended to fall in, lose energy, and cluster, and then form stars.
I'm confused, but that's not inordinate. But
We're here to help.
yes, I essentially think what you're talking about right now is the effects of gravity.
Right.
What gravity does as an effect on an object, right?
Mm-hmm.
So do we really understand what gravity is? Number one, okay. And number two, I get the impression that the bigger the object or the bigger the amount of matter there is, the more gravity it has.
Right.
And somehow now, from what I'm getting from you guys, is that dark matter will affect gravity. Or
I don't think you're confused at all,
No?
actually. No, I think, yeah.
So what we're saying is that we're measuring the effects of gravity in these objects. Okay? So, okay, let me put it this way. Given how far the Earth is from the sun, and given how fast the Earth is moving, and once you know the force law that Newton figured out, and there's a constant in it that you had to measure, then you know exactly how much the sun weighs. If the sun suddenly, its mass cut in half, the Earth would shoot out to a bigger orbit, a slower orbit that's bigger. If the sun suddenly weighed more, the Earth would get sucked into a tighter, faster orbit. So when we look at a galaxy and we measure how fast things are orbiting, we're measuring how much mass there is in the galaxy, given that we assume that the gravitational law is the same as it was for the solar system.
You have large and small galaxies, you have large and small suns. How does that change the gravitational pull? And then, what does the Higgs boson have to do with all of this?
Higgs comes later. So for a galaxy, it's kind of most of the suns in the middle are going to affect how things orbit on the outside. So what the astronomers are able to do, and we're sort of particle astrophysicists, so we don't know how to use telescopes actually. They can measure the amount of light, and they're sort of interested in the aggregate. So the size of the individual stars that are the source of gravity don't matter. If it's all solar mass objects or objects that weigh 10 solar masses, whatever, the amount of light that they put out informs astronomers about how much ordinary matter is there, and therefore what force of gravity you would expect from the ordinary stuff, from the stars.
Well, here we have Fritz Zwicky at Caltech, a very prominent place in 1933, studying the dynamics of the coma cluster and applying the virial theorem, and it doesn't make any sense. 40 years later, Vera Rubin's working all by herself. No one's paying attention to her. So it really hasn't been a mystery for 80 years. It was something that was neglected for 30 or 40 years. How could that possibly be?
Part of the answer is Zwicky's data actually was quite preliminary and poor. And like the amount of dark matter he saw was way off.
Didn't Hubble get the Hubble constant off by like a factor of 3 or something?
Yeah. And so it just wasn't clear it was a real problem at the time. He himself didn't go around thinking this is the big thing I've done. We assign, that's really a little bit ahistorical to say. Zwicky said dark matter and everyone finally realized it. That isn't the way it happened. It's more like once it became a real thing, people look back and said, gee, he kind of noticed it, but his data was so poor because there was so little they knew at the time, and they had basic length scale measurements wrong. This is Dan had sort of mentioned what's behind this. So he said, we understand dark matter now within the context of the whole Big Bang, not just galaxies. In the 1970s, it was just galaxies. And now dark matter has to be thought of in the context of the whole Big Bang. And the Big Bang early on was a dense plasma. And then at some point, the plasma was cooling, and it was just sort of, the universe was just a diffuse gas. And from this cosmic microwave background, this glow of light from the Big Bang, which was in the news this week because there was a new, better measurement of it, that light was uniform to a part in 100,000. So there was a point in time when the universe was just boring, just gas with tiny, uniform everywhere, with some places that were just a little more dense and some places that were just a little less dense. And that graininess was a part in 100,000. This is not quite then. This is somewhat later, but you're just supposed to squint at this and say that's kind of uniform. And some places are a little denser and some places are a little less dense. So now I'll get the movie going. Yeah. So this is the time since the Big Bang. This is 70 million years after the Big Bang. And the places that are heavier, it is sort of like our modern society. The heavier get heavier and the thinner get thinner. I guess the rich get richer. So here's the places that are heavier just sort of gravitationally suck the nearby matter onto them. And the places that don't have matter lose. And this is a simulation. This is a computer simulation using known laws of gravity. And the bottom line is that this simulation matches very, very well when finally this, see the time now we're at 390 million years after the Big Bang. This is a redshift that started at 50 and now it's down to 10. This is eventually basically going to be about one galaxy here with its neighborhood. This is 500 kiloparsecs. That's about 50 times the width of a galaxy. But this is, there's going to be a galaxy at the center there. You see all these small little clumps, and they're kind of getting sucked into this one place that happened to be, well, they made the movie after they'd run the computer simulation, and they found the dense spot. And so then they made the nice fly-around view of that, right? So they've picked a place that was going to be the center, that happened to be the center of this. Now, here's the amazing thing. In this simulation, all there is dark matter. For two reasons. One is it's easier to simulate. It's really hard to simulate normal matter because it does all this weird stuff and it forms supernovas and all this gas, and it's really complicated, okay? But that's not the reason that's the simulation. The reason they simulated the dark matter is because the dark matter is really the only thing that's important here. If there were no dark matter, there would be no galaxies. The dark matter clumped first, and it attracted normal matter to fall onto it. So, well, another reason we're watching this movie is it's really pretty, right? So here we are, the scale's shifted a little bit, so now a galaxy is about the size of the bright white part. And so this is a simulation of the formation of what we think of, we hadn't really mentioned, but the stuff around the dark matter in a galaxy we think of as kind of in a big spherical distribution around the galaxy. We call it a halo. We thought that based on just the way just on that view of the galaxy, the curves I showed earlier, people already back in the 70s and 80s thought it's going to be a big kind of round distribution of dark matter. We don't know what the dark matter is, but that's what it's like. Cut to today, and this is a computer simulation just based on the measured amount of graininess in the early universe, known laws of gravity. This is what dark matter would do. And all our understanding of dark matter, like from the cluster measurements, pretty darn well matches these sorts of simulations. So basically, we are able to calculate why the universe has sort of the number of galaxies it has, how frequent they are, how they're clumped together. All of this stuff just comes from standard gravity and a cocktail of dark matter with a little bit of normal matter. And so our understanding of dark matter is much more than just galaxies and clusters of galaxies. It's sort of the whole story of how we understand the Big Bang mathematically. Dark matter is the starring, at least matter component of it. And yeah, so now it's finished. So imagine that as shown in light, but that is the dark matter around a galaxy. And a galaxy would be kind of a little afterthought, about 10% of the mass sort of stuck there in the center.
The thing is, we don't know what the dark matter is. We kind of know what it isn't. And this ties to the whole story of our understanding of matter. So one of the neat things about dark matter is it sort of ties together the very big, these huge structures that we can study in telescopes, and the very small, the elementary particles. So, we take ordinary stuff, another image off the web. Why they start with a housefly, I don't know. But So you could take a housefly and you could break it down into its constituent molecules, and then each of those molecules is made of atoms. And then the atom has a nucleus in the center with electrons orbiting the outside, and that's what gives us chemistry. And then if we look inside the atom, inside the nucleus, it's made up of protons and neutrons. And then if we even look inside the protons and neutrons, they're made of quarks. So our modern understanding of the basic constituents of matter are the quarks, which come in 6 different types, up and down, charm and strange, top and bottom. And then the electron is a member of another class of particles called the leptons. The electron has an associated neutrino, which is a very light particle with no electrical charge, passes right through us. And then the electron has 2 heavy cousins, the mu and the tau. They each have a neutrino. And then the forces among these particles are communicated through the photon, the gluon, the Z boson, and the W boson. And that combined with the Higgs, which was sort of the last piece of that story, is everything we know about matter that we can study in the laboratory. Okay, that embodies our full understanding of matter at its most basic level. And this goes back to studies that were done in the 60s or 50s even with bubble chambers. This is not the full story. We know from our cosmology studies, studies of primordial clouds of gas and whatnot, that there is not enough of this ordinary stuff to make up the dark matter by a ratio of about 1 to 5. And so an understanding of what the dark matter could be, just what hypotheses might be reasonable based on our understanding of elementary particle physics. The question is, what sort of particle physics could we apply to the early universe to think about what other forms of matter could be made, and could one of those forms naturally be the dark matter that we're looking for?
This is a slide just to kind of orient ourselves in terms of thinking about matter. And the point is, in sort of our modern quantum mechanical view of the world, a particle is sort of 2 components. There's some point-like mass, and point-like means, as far as we can tell, they're sort of infinitely small in extent. And exactly how infinitely small, we don't kind of get. I mean, if it's truly infinitely small, what in the world does that mean? But we can tell by what we've seen in atom smashers that the mass seems to be contained for the fundamental of these particles, the quarks, neutrinos, electron, that mass is all in a tiny spot in the center. And then also going along with it is a force field. And the force field determines its size, and the force field and the mass are not really logically related. We're used to thinking something that's big is heavy and something that's small is light. There's exceptions. A balloon is big but not very heavy. But at the quantum mechanical, at the particle level, they're just utterly different, okay? So for instance, there are force fields. There's 4 forces we know about. There's gravity, and it has essentially a very weak force field that has some huge range. Then there's electromagnetism. It has a range which is the size of an atom, okay? Why is an atom as big as it is? Why are the molecules in your body as far apart from each other as they are? That's the range of the electrical force field, effectively. And it's kind of got a moderate strength. The nucleus, where these protons, which would electrically repel each other, are bound together and stuck with neutrons. There's a really intense force field, much stronger than the electric force field, but it only has a very, very short range. It has about 1/millionth the size, the range of that force field, as an atom has. 10 to the minus 9 meters for an atom, and 10 to the minus 15 meters for the nucleus. And then we know that there's a weak force, which is kind of fairly weak in one sense, but also incredibly restricted in its range, because the force carrier for it is very heavy. But in any case, it's very tiny. So the mass is independent of the forces. Here kind of is a little cartoon of that. You can think of blue as being, say, an electron or a proton. with this big force field. It's an electric force field, and it's not quite so intense. And this might be a strong force. These aren't quite to scale, but you know, it's fairly intense, but with a limited range. And this might be a weak force with a fairly small range and some moderate intensity. And even a single particle can have different forces all at the same time. So an electron has an electric force field, no strong force field, and it has a weak force field. And if it comes by a quark, the quark has an electric force field and a weak force field, but they're going to communicate through their electric force fields. If a neutrino comes along, that's a particle we know about, it only has a weak force field. Now all of it has gravity. The gravity is kind of irrelevant, it's so weak. And so from the point of view of an electron and a neutrino, the neutrino doesn't care that the electron has an electric force field because the neutrino just doesn't know about it. And so then from the point of view of those two particles, they're effectively really, really tiny. So you often hear this statement made that seems paradoxical, one of these weird like paradox statements about science. Matter is mostly empty space. I think that's just a horrible way to talk about things. Matter, of course, is not empty space. Matter is composed of things that are held together by electrical force fields, and those electrical force fields completely fill the space between things. But if a particle comes along that doesn't have the electrical force field, it only has the weak force field, it does see space as mostly empty. Okay, so that's what it would mean to have a really, really tiny particle, and that's what we think the dark matter could be. We have the idea that they're WIMPs. They're objects that have a weak force field but a very large mass, about the mass of an atom. So weakly interacting massive particle. That's the kind of the most popular theory, one of the more plausible theories as to what the dark matter is. It's something like a neutrino, but heavy. How small is a neutrino? You go to the dentist and they X-ray you and you put a little lead to shield yourself. The little lead apron. It's about it's a 1/16 of an inch or less of lead. 32nd of an inch of lead will stop an X-ray. If you want to stop a neutrino with lead, you need a light year. And then you kind of got about a 50-50 chance of it bouncing off once. That's how small a neutrino is. And so we think the dark matter would be a particle like that, but it weighs as much as one of the very heavy particles we know about, the W or the Z, or basically as much as like a heavy atom, a gold atom.
Comparing the solar system to the galaxies, and you're saying everything in the solar system from very small to very large all seems to follow the same law, but when you're looking at galaxies, it seems very different, which is why we're looking at dark matter as an explanation. The one difference between the solar system and the galaxies is time. We're looking at the solar system, basically everything in the solar system happens within hours, maybe days. When you're talking galaxies, you're looking back in time. Do you see any correlation when you're looking at galaxies that are further away, that the velocities are different, that there's more dark matter, to say, in older galaxies, and newer galaxies don't need to have as much dark matter, and that could be an indicator that the laws of gravity are actually changing as opposed to more dark matter? Has that been looked at?
So the question is there sort of time evolution over the history of the universe? Solar system is kind of this immediate thing. It's close by, so it's recent, even present. And as we're looking at galaxies further and further back in the Big Bang, are we seeing some time evolution in the properties? I don't know the answer to that question. I know people have looked at time evolution of fundamental constants, but we've not seen any evidence for that. I don't know how far away a galaxy can be where we can still study its dark matter component in a conventional way.
Do we know the mass and density, how many neutrinos are out there and how much they weigh, since they're so hard to measure? Could they be the dark matter?
We know enough about neutrinos to know that they're a minuscule contribution.
Yeah.
Yep.
People thought they might be the dark matter up till the mid to late 80s.
Galaxies with spiral arms and dark matter being in the galaxy, wouldn't the dark matter create the galaxy as a smooth disk rather than having these uneven arms?
I think that the reason galaxies are all weird and complicated has to do with the normal matter in the galaxy. think the dark matter just kind of created this nice environment for the normal stuff to go into. And then it did, I don't know about, you'll have to ask an astronomer why you have like a barred arm. There's all sorts of weird shapes of galaxies. I think that in general, the dark matter background is kind of thought to be fairly uniform. And then the normal matter does this weird stuff, like if two galaxies collide. There's also a whole story about, the normal matter came in and why didn't it sit in kind of a roundish thing? And the answer is that light could be emitted such that it could kind of, it sort of frictionally collapses down, and it's left with one amount of angular momentum that keeps it rotating. And that whole process, you just didn't see that in that simulation because the dark matter doesn't do that.
So the hypothesis that we're testing is that these WIMPs, these weakly interacting massive particles, would have been produced in the early universe. They would have been clumped in some, overdense in some regions, less dense in others. The denser regions, just again from the happenstance in the early universe, would already be gravitationally bound. So the expansion of the Big Bang would be taking place, but the stuff that was already bound wouldn't be pulled apart very much by the expansion. And so these clumps would be there, and the galaxies, what we think of as the galaxies of the normal matter, would have fallen in. And so this is what sort of our picture of a galaxy looks like. There'd be a halo of dark matter, and this is just a cutaway. It's really supposed to be a whole sphere of a dark matter halo. And then what we think of as the galaxy would be this disk of stars in the middle. And the idea is that a given WIMP would be just another object orbiting in the gravitational well of the galaxy. And if we stick a detector in its path, then maybe occasionally one of those WIMPs would scatter from something in the detector and make itself known to us. And so this is the hypothesis that we're testing. We get some clues about what the property of the WIMP is from how it would have had to behave in the early universe to still be around and be the dark matter today. And so that's the hypothesis that we're testing. And we did questions already. So now we just go on to tell you about the Lux detector.
So this is a cartoon of the way our detector works. There was a WIMP particle that came in. So what you're looking at is a cartoon of a detector. It's like a Geiger counter. I'm going to let the movie run a couple of times. And the WIMP basically, because it's we're all worried about a meteorite hitting the Earth, and why? Well, because the meteors are, in general, anything from outer space is going fast, okay? These WIMPs, which are orbiting not kind of with the solar system, but just randomly, they're going very fast. They're going about 1,000th the speed of light. And so if they hit a particle, just because, even if it's tiny, occasionally it'll hit an atom, it causes a lot of disruption. But it's about like an X-ray hitting your body, okay? And how do we detect X-rays? Well, you have a material where you can see the disruption when a higher energy particle smashes into it. You can't just see an atom just sitting there. You can't just see a WIMP. If we had a cup full of WIMPs which were just sitting here at rest, you couldn't detect them. But they're coming in at high energy and they cause disruption. So, the movie started again. So, okay, so this is a vat of material. In our case, it's liquefied xenon gas. And the WIMP comes and it strikes a xenon atom. And xenon is a material that has a flash of light when it's struck like this. And we saw the light. And then electrons are ripped off of atoms, and they're pulled up. And they're pulled up out of the liquid, and you get a second flash of light. So what is xenon? It's a noble element. There's helium, neon, argon, krypton, and xenon, and radon. But you wouldn't make a detector out of radon because it's very radioactive. Those are the noble elements, and you can liquefy them instead of being gas by cooling them. And you can make a nice detector. Notice when this electrons get pulled out, they make a flash of light, and it's sort of the top and the bottom of this detector are arrays of what are called photomultiplier tubes. They're very fancy detectors that measure light. They're like what's in your digital camera, but they can see single photons very, very easily. And in top and bottom, we measured the first flash of light, and then when the second flash of light from these electrons coming out, we can tell where laterally that happened by the pattern of the light. And then we can also tell how deep the event was because there's a time difference between the first flash of light, boom, this is a time axis, that first flash of light, oh. And so we can tell where in the detector this particle struck it. And there's all sorts of radioactivity coming from the outside, and the WIMPs will randomly hit anywhere, often in the center, and the radioactivity, we hope, is not in the center. And because we can see where the event was, we can hopefully distinguish WIMPs from non-WIMPs.
We'll say a little bit more about one of the challenges in any measurement is the signal and background. So Tom's described how the signal would show up, the WIMP would come in, scatter, flashes of light, and we put those patterns together. But the whole idea of signal and background is really critical here because most of the WIMPs are going to pass right through the detector and never be seen, right? You could have light years of lead and most of them would go through. So the way I like to try to get across the idea of signal and background is like astronomers figured out very early on you should do astronomy at night because that's when you can see the stars, right? But the stars are still on during the day, right? No one switches them off. But you don't do astronomy during the day because the atmosphere scatters sunlight. And so the scattered light completely overwhelms the starlight. So we have the challenge of how do we make our background go away? How do we get rid of all of the radioactivity that's just in materials around us and cosmic rays? How do we get rid of that background so that this very weak WIMP signal will show up in our detector? So the detector itself, this tank of xenon that Tom showed you in that animation, is a real thing that lives inside this tank. Some of the shielding that we get against background events comes from just knowing where the event took place. Right? So Tom was describing that WIMPs will interact throughout the volume, backgrounds will tend to interact in the outer edges. So we do everything that we can to make the detector itself as clean as possible. But there's still a lot of radioactivity in the environment. So the Earth's crust is about a part per million uranium and thorium. And this would just give a very high rate of other known particles impinging on the detector and light it up like a Christmas tree, and you'd never be able to see a WIMP. So we put the detector inside a water tank that's about a radius of about 4 meters. And that water is purified using commercial technology. And any radioactivity that's coming from outside the water tank will tend to get stopped. It'll just get absorbed in the water. And so that's a good thing. Then the experiment itself is a mile underground in a former gold mine, a Homestake mine in South Dakota. The reason that we go underground is at the surface of the Earth, we're continually being bombarded by cosmic ray particles. So these are probably remnants of supernova, high energy particles. If you stick out your hand, you have about 1 cosmic ray muon going through your hand every second. The rate at which that we expect WIMPs to interact in these detectors is exceedingly low. So if you tried to run an experiment at the Earth's surface, the cosmic rays bombarding your laboratory, again, would create so many background events that you'd never be able to tease out a WIMP signal. So these are some of the measures that we go to.
So this is just some pictures of the detector. I showed you the movie cartoon of how the detector would work. This is a photo of the detector when it was nearly finished being constructed. It's a little hard to see. Everything that was in that movie, unfortunately, is inside of what's in this photo. You're seeing a sort of plastic casing around the region in the center, which is about 1/2 meter tall and 1/2 meter diameter. So 2 feet by 2 feet, roughly, of volume. It's just a cylinder bucket where the liquid xenon will be. You see this copper here, this orange color. That's a copper piece and a copper piece. Inside of those, there's a big thick pieces of copper that have sort of a honeycomb of holes where those photomultiplier tubes are. They're like old-fashioned TV sets, basically, each of them, in terms of what they look like, a little vacuum tube. And there's a whole array of them on top, a whole array of them on bottom. And then all of this is housed in a can made of titanium. Titanium turned out to be low in radioactivity. Everything in here has been measured to have very low radioactivity. The radioactive environment here is something like 1 billion times quieter than us, than the room, okay, in terms of less radioactivity. And then it's sealed up, and then that copper can. The whole thing is cooled down to about the lowest temperatures like that you would normally record. That we could maybe run this experiment just out like in a cold day in Siberia, okay, like lowest record temperatures, about minus 100 Celsius. But we cool it with liquid nitrogen. Then there's a vacuum can, so another titanium can, and here you're seeing both of those cans sort of sealed up. And this is inside of the water tank. That artist's conception that you saw before was something we created about 3 or 4 years ago, and this is roughly in December. Here's a student. This was a publicity photo that was taken at the lab where we are. That fellow is a graduate student at UC Davis, but he actually was an undergrad that worked here in my group at Case and graduated a few years back. And he led actually the effort to do the final installation, and he ended up getting in the photo. So there we can see this big tank of water. Those are photomultiplier tubes as well. If the occasional cosmic ray, when it goes through the water, it creates a little bit of what's called shrink-off light. So we can even tell that a cosmic ray had a near miss. Or if it hits the detector, it'll light the detector up. It happens like once a day at this mile deep depth instead of once a second in our hand.
So we don't do this work alone. Science at this scale, sort of medium scale physics, requires collaborations. So our collaboration is about 80 active members, groups across the country and also in Europe. And we get together a couple times a year en masse for a collaboration meeting. And this particular meeting, about once a year, we'll have our meeting at the Homestake Mine in South Dakota. So in the background there, this is the head frame that runs the cage a mile underground. It's about an 11-minute ride. We do it just like the miners did, hard hats and lunch pail and all that. And it's just been a great community. Prior to the lab hosting sort of a modern generation of experiments, they ran a solar neutrino detector for about 30 years. Ray Davis won the Nobel Prize it was like 2002 for discovery of neutrinos coming from the sun. And recently the lab finished outfitting this same cavern for us to perform the Lux experiment in. So we hope it's a lucky spot.
A little bit about the sociology of doing these experiments. What it's like working in a big physics experiment. Everyone thinks they're really smart. It's sort of like herding cats. Everyone comes together and argues about who's smartest, and no one is really in charge. And it's almost impossible to get fired from a collaboration like this. If you join, you're kind of in. There's no way to vote anyone off the item. Yeah. Most of us are socially awkward. So it could be a bit of a challenge, but occasionally we get things done.
Thank you.